So, welcome to this class on hardware security. So, last day we started to discuss about side channel attacks. So, in particular we shall be trying to look into one of the very or most popular forms of side channel analysis, which is known as power analysis in today's class. So, we shall initiate this topic, and today we shall be trying to kind of go through the working principles of differential power attacks, or DPA as it is called. We shall try to give a toy example to explain how it works, and we would like to talk about difference of mean, which is a very popular method and classical method of doing DPA, and try to see how DPA can be or DOM can be applied on AES, which we have studied previously in the class. So, as we have already discussed, there are two forms of power attacks, broad categories of power attacks. We have got simple power attacks, where the fact which is exploited is that power consumption depends upon the underlying operation, okay, like whether it is squaring or whether it is multiplication or whether it is addition or doubling. So, the idea is that the power consumed depends upon the operation. So, if the architecture or if the implementation is very naive, then often it may happen that you have different branches in your execution, and where you are doing different operations. Okay. So, therefore, right, if the power consumed depends upon the operation, then that would imply that if you have a very accurate measurement of power consumption, then you would have an idea about which operations are being taking place, and therefore, you know the execution path of your program. Okay. And if your execution path is dependent upon some secrets, then the secret can trivially leak. So, that is the idea of simple power attacks. On the contrary, right, you have got an even more powerful adversary, which is called as differential power attack, where the fact which is exploited is that power consumed depends upon the underlying data. So, therefore, right, even if you protect your designs against simple power attacks or SPA by, say, like doing always the same operations, right, even then DPA can work, because DPA would fundamentally depend upon the operations which is being done, okay, like rather the data on which the operations are being done. So, therefore, you would probably get an idea about like what your multiplier is operating on, what your squaring is operating on, or what your doubling is operating on, or what your addition is operating on. So, and if you have got an idea about the intermediate data, then you can do like or follow it up by cryptanalysis to get the actual secret key. Okay. So, DPA is a very powerful attack model, and what we have seen is that it can lead, and as we will see in more details in our class, is that it can lead to very efficient attacks against implementations. Okay. So, therefore, right, as I said already, that SP or simple power analysis directly interprets the power consumption of the device, and it tries to look for the operation which takes place and also the secret key. Okay. So, therefore, often in the trace the secret key is evident. Okay. So, what is a trace? Because we will be using the word trace several times. So, trace is nothing but a set of power consumptions across a cryptographic process. Okay. So, often we basically have something which is called as a triggering signal, which is used to kind of indicate the initiation and termination of a specific cryptographic operation. Okay. And then the set of power consumptions which you essentially kind of accumulate during this period when the actual crypto operation is being done is called as a trace. Okay. Note that we are not actually measuring the trace of only the cryptographic operation, but rather we are measuring the trace of the total chip or the power consumption of the total chip, and then we will try to statistically kind of correlate that power with your underlying data. Okay. So, for example, let us take an example, like suppose if we have got like a 1 millisecond operation, that means the total duration is 1 millisecond, and if you are sampling it at 5 megahertz rate, like if your oscilloscope is sampling at a 5 megahertz rate, then you will have a power trace which will have 5,000 points. Okay. And therefore, this kind of observation or of real data, which essentially could be in milliwatts or microwatt depending upon your power consumption, right, and if you are plotting that across 5,000 points of time, then essentially this statistics which you collect or accumulate is called as a trace, is called as a power trace. Okay. So, now our objective will be that we will try to utilize this power trace. Okay. So, now therefore, let us so as we have kind of had an idea about what an SPA essentially means, we shall in particular try to look what DPA means actually. Okay. So, as I said that in DPA the assumption is that the power consumption depends upon the underlying data. Okay. So, here is a very simple example to illustrate that this principle or the principle on which DPA is based has got nothing inherently to do about the algorithm. Okay. So, rather if you take any binary encoding of information of data, you will probably find like that that why DPA works. Okay. So, let me take a very simple example of say a 4-bit state of some arbitrary algorithm. Okay. And then let me observe the Hamming weight of the state S. Okay. So, as you can see, right, that I have kind of varied S from for all these values, like for example, since S is a 4-bit value, there are 16 possible values. Okay. So, I have taken all the 16 possible values and I have observed the Hamming weight in this column. So, the Hamming weight means the number of ones which are there in the state. Okay. So, for example, in the first state, which is 4 zeros, there are no ones. So, the Hamming weight is 0. Okay. In the second state, right, you have got 0 0 0 1. So, there is 1 1. So, the Hamming weight is 1. Okay. Likewise, if you go to 1 1 1 1, right, the Hamming weight is 4 because there are 4 ones. So, why do I observe the Hamming weight? Now, because you will see that in VLSI there are different power models. Okay. So, the objective of a power model is try to get a hypothesis of the power. Okay. Of course, power consumption is a very complex manifestation of several things, but what has been found is that a major contribution comes from the inherent encoding of the state. Okay. So, the idea is that there are different power models like Hamming weight, Hamming distance. Okay. Some of them we will see as we progress in the class, but a very simple power model is what is called as a Hamming weight power model. The idea is that you take the state and try to see the number of ones. Typically, you will see that the power consumed will be proportional with the Hamming weight of the S. Okay. Of course, there are other noise terms and there are other aberrations and things like that, but it has got a proportionality. So, it has the proportionality is with the the Hamming weight of the S. So, we can write this also in the form of a formula like the power consumed at say for example time t, you can write that as say like alpha, which is a constant, into say the Hamming weight of your target state plus some noise term. Okay. So, this noise term is say denoted as NT. So, this could be a Gaussian noise. Okay. But this is essentially what I am meaning as the power model actually. Okay. So, you can actually like virtually simulate a power model also using this model. Okay. But in a very simple setting, assume that the Hamming weight is representing your power model. That means, when the Hamming weight is increasing, I am expecting that the power will be more. When the Hamming weight is less, then I am expecting that the power will be less. Okay. So, this is a very simple setting. So, in this setting, right, if I observe, then that means that this column or the Hamming weight column is kind of indicative of your power consumption. Okay. So, now if you observe the target bit of the state S. Okay. So, you can see that this column stores the LSB of state S. Okay. So, the LSB of state S is sometimes 0, sometimes 1, sometimes 0, sometimes 1 and so on. So, it kind of alternates, right. So, now I do a very simple exercise. The exercise is as follows. I take 2 bins. Okay. So, I call one of them as say 0 bin and the other one as 1 bin. Okay. And I take a particular power value say Hamming weight of S, okay, indicated by Hamming weight of S, and put that either in the 0 bin or in the first bin, depending upon whether the LSB is 0 or not. Okay. So, I put it in the 0 bin if the LSB is 0, I put it in the 1 bin if the LSB is 1. Okay. So, therefore, you can easily see that the first Hamming weight S here, HWS, will go to the 0 bin, right. So, 0 goes here. Next, you have got HWS is 1. Okay. So, this goes to the 1 bin. Okay. Next, you have got another one, but this one now goes to the 0 bin. Okay. The next 2 goes to the 1 bin. Like this, right, you basically start accumulating and you have got out of 16, this 0 bin will have 8 corresponding components and the 1 bin will also have 8 data. Okay. And now, I basically take an average of all these values and I take the average of all these values. So, these I call as 2 means, okay, say mean 0 and mean 1, and I take the difference of these things, right. I take mean 0 minus mean 1 and this is what I call as the difference of mean or DOM. Okay. So, it turns out, and you can check that later on, that the data which is over in the 0 bin and the 1 bin, you will see in that one of the bins the number of if you add up those values, they will add up to 20, and therefore the other one will be 12 because the sum will be 32. Okay. So therefore, if I take the difference of mean will turn out to be 1 in this case, which is a non-zero value. Okay. But at the same time, observe that the total sum is 32, right. So if I add up these things, I will get 32. Now if the split was purely random, then I would have expected the expected sum of 0 bin and the expected sum of 1 bin, both of them would be 16, okay, because each of them, suppose it goes with like to the 0 bin with a half probability and to the 1 bin with also a half probability, then I would have got this 32 split exactly into 16 and 16, or at least around 16 and 16. Okay. So that means the difference of mean would have been 0 in that case. Okay. So that means if we are basically splitting, right, depending upon the S, which is essentially the like the LSB of S, for example, then you find a non-zero difference of mean. Whereas if you kind of split like randomly or do a random partition, then the difference of mean is 0. Okay. So that means if the fact that you are splitting the Hamming weight of S, okay, depending upon or correlated with some kind of state bit of S, okay, can easily be distinguished whether with respect to like whether you are doing the splitting in a random fashion. Okay. And that essentially tells you that there is an avenue of attack. Okay. For example, like if you want to see that if you just do this splitting in a random fashion, okay, then this is how it look like. So like if I just partition based upon so this partitioning has been done by rand function, okay, which is not necessarily a great random number generation, but suppose we use that as for the splitting, then you will find that the difference of mean, right, gets close to 0 as we accumulate number of samples. Okay. On the other hand, when you are doing the partitioning with respect to a correlated bit, that means for example the LSB of S, it could be any other bit of S also, it could be also the like XOR or exclusive OR of these bits as well, you will find that the difference of mean will get to some non-zero values. Okay. So this you can like try to also imagine that this has got the you can basically use it to essentially bound a simple conceptualize a simple difference of mean attack. Okay. For example, suppose like you have got an intermediate state S. Okay. So this is a state S, and this you follow up with some kind of S box. Okay. So there is an S box as we have seen already in context of AES to AES, for example, and then I do an exclusive OR with some secret key, okay, and I generate the cipher. This is my cipher. Okay. Cipher denoted by say C. Okay. So now what I will do is I will try to guess this key. Okay. So there are just imagine that is a very small and hypothetical example with say like 4 bits of S box. So there are several 4x4 S boxes. Suppose I take one of these 4x4 S boxes and make a very simple cipher. Okay. So what is the total key size space? Therefore there are 2 to the power of 4, that means there are 16 possible key values, and if I just give you the cipher, you cannot tell me like that which of them is correct. Okay. But now I also give you the like suppose I give you this the Hamming weight of S. Okay. That means you get essentially observe the power consumption, and imagine that the power consumption is nothing but the Hamming weight of S. Okay. So now what you will do is you will guess this key. Okay. So you will make a guess for this key, because you know that any one of them is possible. Okay. But observe that if I don't give you this powered information, you have got no way to understand whether this guess is correct. Okay. Now what we will see is that with this power, right, with this powered information, you can distinguish between the correct guess with the other wrong ones. How can you do that? You will guess this, you will XOR with the cipher, you will take the inverse S box. Okay. So if you take the inverse S box, you will come to this state S. Okay. So imagine that I just take the LSB of S. I basically take the inverse and I just find out what is this LSB. Okay. And now I essentially do the splitting as I told. So I will do the exercise for all the HWS values and I will split them. Okay. If my guess was correct, then that means I have correctly predicted the state S LSB of S, and therefore my partitioning will essentially take place just as we have seen. On the other hand, if my guess was wrong, that means for all the 15 wrong cases, I will find out that this will sometimes match, will sometimes not match, because then this function, okay, which is also called often as the selection function, okay, will essentially operate as a random number generation, or will be like a pseudo random function generator more correctly, and therefore, right, you will find that this partition, the partitioning of the power traces will be in a random fashion, okay, and therefore the difference of mean will be close to 0. So therefore, this fact that for the correct guess you will have a high difference of mean, okay, versus for a wrong guess you will have a small difference of mean, can be utilized as a distinguisher, okay, that distinguish the correct key from the wrong keys, okay. So this is basically in a very simple terms, like an explanation of how it works, and now let us see some more concrete examples to understand how it can be applied to ciphers. So first let me start with a very toy cipher, okay, a toy example. So this example is of the, again a reminder of the RSA algorithm, because I am just taking an exponentiation routine, okay. So the exponentiation routine is nothing but denoted as z equal to y to the power of x mod 256. Again, this is a toy example, so 256 is really a small number for practical settings, but imagine that I want to know this x, okay, and assume that x is also an 8-bit value, okay, and assume that the attacker can start with x7, x6 and whatever, right, till x0, and suppose it knows the first 4 bits of x, okay. So the attacker knows the first 4 bits, and again like that Kacher, like the Kacher's attack that we have seen, my objective is to guess the next bit, okay. So the probability of guessing the next bit with no side channel information is half, because I have no way to understand whether it is 0 or whether it is 1. So now we assume that the attacker varies y, that means the attacker kind of changes the value of y and obtains several power traces. Like in Kacher's attack we are observing the timing, right, here we are observing the power signal. So we can like simulate them in a setting just to understand by Hamming weights, okay. So that means I can simulate, remember that in the square and multiply algorithm there is a state s, right, which I am either squaring or I am multiplying with y, okay. So what I do is that I kind of monitor the value of that state s and I plot the Hamming weight of that state s as an indication of the power value, okay. So therefore I observe the Hamming weight of that state s, which I am like so in the square and multiply algorithm I always do a squaring, and if the key bit is 1, that means if the key I or the ith bit is 1, then I multiply s with y. That was essentially my, so again all these equalities are modulo 256 in this case, right. I am doing mod of n where n is a simple 256. So therefore, right, when I am doing these operations, right, when I am doing these operations, I suppose monitor the Hamming weight of s. The objective is that this gives me an indication of the power consumption of the algorithm or of the circuit. So therefore, right, with this example, so now let us see like how we can do the attack. For a given y, the attacker now guesses the next bit and computes the probable s, okay, after the third iteration, okay. So note that the square and multiply starts from bit 6 down to 0. So you are going from bit 6, bit 7, bit 5 and so on till bit 0. So therefore, right, now based on the LSB of y, the corresponding trace is put into the 0 bin or the 1 bin, okay. So here when I am saying the like the so basically the idea, so maybe like you can say that I am using y also as s, but for clarity probably you can think of this as based on the LSB of the running variable, okay. So that is probably this would be better to say that this is the LSB of s, okay, because what I am doing is that I am initializing s to y and I am then squaring every time, and if the ki bit is 1, that means if my secret is 1, then I am multiplying s with y, right, to get y power of x. So therefore, right, what I am observing, so when I am like I am observing the probable s after this iteration, okay, and then I am splitting my or putting that corresponding Hamming weight s, right, which is my power value, into the 0 bin or into the 1 bin, depending upon what is the LSB of this s. Note that I do not know as an attacker whether this bit was 1 or not, right. So the probable s can be after the value of s square, or it can be because of s square and then multiplied with y. So I have got no way of understanding that. But right, in the simulation, since I am observing the power value, the power value is with respect to the actual correct key. So therefore, right, the power that I am getting is with respect to either like s square or after s square has been multiplied with y. Okay. So but when I am guessing, right, then the ambiguity from the attacker's point of view is that, okay, I have got this power value, whether I will put that into the 0 bin or whether I will put that into the 1 bin. So that depends upon its guess. So because the attacker will guess, and there are two choices of the guess, right? It is either 0 or it is 1. So if it is 0, then the attacker calculates s square and finds out the LSB of s square, and depending upon that it does the splitting. Okay. And if the if the guess is 1, right, then it basically calculates s square, multiplies with y, and again takes the LSB and then splits. Okay. So now which one is correct? That is the question from the attacker's point of view. So therefore, what the attacker does is that for every guess, there are two guesses, the difference of mean is computed. Whichever is the the higher value of difference of mean is a probable guess. Okay. Of course, this is a statistical attack. So therefore, what it implies is that if you observe large number of samples, then you are expected to get a better result, okay, and or clearer separation. So here is a simulation that we ran. In this case, the correct key is 0x8f, and therefore the next bit is 1. Okay, remember that I know the first 4 bits, right? So therefore, I know I know the first 4 bits. So I know that it is 1000. Okay, and then I have got 4 ones in the correct key. So therefore, right, I mean what I am trying to say is that my this is my secret key, right, and then I have got f. So therefore, I mean I have got f. So basically I have got 1 1 1. So that is 4 ones. Okay. So therefore, what I know till this point, the attacker does not know this. So the attacker wants to know this. So therefore, the correct next bit is 1. Okay. So now you observe that this is there is a wrong guess and there is a correct guess. So this one is for the wrong one. So this is the wrong guess. Okay, and this one is the correct guess. Easily you can see that in the correct guess there is a very significant difference of mean peak. It is kind of 0.9 versus 0.2 with something like 2 to the power of 10 traces. You can observe more to get a better separation. Okay. So therefore, right, it indeed kind of tells me that a simple difference of mean attack works in this setting. Okay, and it should work. And likewise, right, you can also think of extending these attacks. So and kind of formalize how it works. Okay. So the basic idea of difference of mean was introduced by Paul Kacher, okay, and in a 1999 paper, and his colleagues. So it is more powerful, as I said, and different and more difficult to prevent than SPA. Okay, and there are different power consumptions for different states like 0 or 1. Okay, so the idea is that it basically kind of relies upon this assumption that power consumption varies with data, whether it is processing 0 or whether it is processing 1. Okay, that means when I am saying it means typically the internal gates of your circuit. Okay, so it could be in a very simple setting, an AND gate, for example. Okay, an AND gate is operating upon 2 data, say x and y, and ANDing them. It could depend upon whether you are operating on 0 or 1. Okay, if we even simplify it, let us consider an inverter, for example, a CMOS inverter. So whether you are whether you are operating on 0 as an input or whether you are operating on 1 as an input, your power consumption will vary. Okay, and since it varies, right, you find out a manifestation that the power consumption depends upon the underlying data in our normal technology, and that is exactly what is being exploited in these attacks. Okay. So typically these attacks have got data collection phase and data analysis phase. Initially you should accumulate power traces, okay, and for that you need an experimental setup, okay, and I will try to give an overview on the experimental setup in the future class. So you take an overview, I mean you basically collect your power traces in an accurate setup so that the noise is less and the quality of the power traces is high. Okay, and then you have got a data analysis phase where you basically try to analyze the information which you have collected. So the procedure is very simple. You basically gather many power consumption curves, okay, so typically few thousands for ciphers, and then you assume a key value. So basically you guess the key. So remember that if you have got a 128-bit key like you have in AES, you cannot guess a 128-bit key, because if you do that, right, then your worst case key complexity can be 2 to the power of 128, and therefore you don't have any advantage over a brute force attack. On the contrary, right, this attack is very powerful because you can do that in a divide and conquer manner. So you can basically guess parts of the key, okay, and then you can combine this information. So you can recover the key in a byte by byte or a nibble by nibble fashion. So it's very powerful in that sense. And what we do is that you basically divide into groups. So in the difference of mean attack, which is the most probably classical form of doing a DPA attack, you basically divide the data into two groups, a 0 bin and a 1 bin for the chosen bit, and you calculate the mean value curve for each group, okay. And then the idea is that if your assumption or if your guess was correct, then you will get a non-negligible difference in the differential curve, okay, and that essentially will distinguish your correct key vis-a-vis the wrong key. Okay. So that is essentially the idea of DPA, and what we will see in the next class is how you can do a DPA attack on AES. Okay. So let me stop at this point and we will continue on the DPA on AES in the next class. Okay. Thank you.